Hello student, how are you? Welcome from my channel The Learn Physics. Today I will be discussing the second chapter of NCERT class 12. Now today's discussions are the potential due to a point charge, due to a dipole, due to a system of charges, equipotential surface and its properties, potential energy due to system of charges, potential energy in an external electric field, conductors and capacitors, parallel plate capacitors, combination of capacitors, energy stored in capacitor, and the numericals of all topics from the NCERT book. Now let's start. First of all, potential. Potential is the amount of work done to bring an isolated unit positive charge from infinity to a point in the gravitational field. Now look at this. Charge Q is at a distance r from the point P. We have to calculate the potential at the point P. So the potential at the point P is the amount of work done to bring an isolated unit positive charge from infinity to this point against the electrostatic repulsive force. So now first of all, the intensity at P due to charge Q is E equal to Q divided by 4 pi epsilon naught r square directed away from the charge Q. Now amount of work done to displace the unit positive charge by a distance dr towards the charge Q is force into displacement. Now this work done becomes negative sign of E into dr. Look at this, the direction of E along this direction but displacement opposite to this direction. Therefore the work done becomes Q divided by 4 pi epsilon naught r square into dr with negative sign. So potential at the point P is V equal to integration of from infinity to r is Q divided by 4 pi epsilon naught r square dr with negative sign. Now look at this, this is the negative Q divided by 4 pi epsilon naught, this is r to the power minus 2 dr integration infinity to r. Okay, now V equal to minus Q divided by 4 pi epsilon naught. Okay, this is the r to the power minus 2 plus 1 by minus 2 plus 1 and this is the r infinity, and finally we get Q divided by 4 pi epsilon naught r is the expression of potential at the point P. Okay, understood? Now the potential at a point does not depend on path. It depends on initial position to final position. So potential is a state function, not a path function. Okay, look at this, charge Q and Q are separated by the distance to r. We have to calculate potential at the midpoint, a line joining this and this. So potential at P, look at this, due to this charge is equal to Q divided by 4 pi epsilon naught into distance, that is r, and potential due to this charge is also Q divided by 4 pi epsilon into r. So this is the 2Q divided by 4 pi epsilon naught into r is the potential at the midpoint due to this and this charge. Now if one charge is negative, suppose this is the negative, then potential due to this charge becomes minus Q divided by 4 pi epsilon naught r, and due to this charge plus Q by 4 pi epsilon naught r. So net potential at this point is 0. Understood? Next, look at this. This is a spherical shell of radius r. You know the intensity inside the spherical shell is zero because charge remain on the surface. Inside the surface there is no charges. As intensity zero, so potential within the spherical shell remain constant, and this magnitude of potential is Q divided by 4 pi epsilon naught into R. Okay, look at this. At every point inside the spherical shell, potential constant, and this equal to Q divided by 4 pi epsilon naught R. Okay, now here condition R less than equal to capital R. Now outside the spherical shell, the potential is Q divided by 4 pi epsilon naught into R, where R greater than capital R. Okay. Now if we draw a graph between V and R, the graph becomes, look at this, the constant within the spherical shell, that is the R equal to R, and outside the surface, this is the charge by distance. So this is the V proportionate 1 by R. Okay. Now for non-conducting sphere, charge remain within the surface. So due to non-conducting sphere, the potential outside the sphere same as that of the potential due to spherical shell, that is V equal to Q divided by 4 pi epsilon naught R, where R greater than equal to capital R. But inside the spherical shell, the potential V becomes Q into 3R square minus R square divided by 8 pi epsilon naught into R cube, where R less than equal to R. Now if we draw the graph between V and R, this graph becomes here. Okay. Now at this point, potential is Q divided by 4 pi epsilon naught R, but here this point the potential becomes 3Q divided by 4 pi epsilon naught capital R. Okay, understood? Next we look at this NCERT 2.1. Look at these two charges, 5 into 10 to the power minus 8 coulomb and minus 3 into 10 to the power minus 8 coulomb, are separated by a distance of 0.16 meter. We have to calculate the position of points where potential is 0. As potential is a scalar quantity, so potential due to positive charge is plus and potential due to negative charge is minus. So look at this, the position of zero potential somewhere becomes here, this is the P1, and somewhere becomes, look at this is the P2. Now first of all we have to calculate the position of P1. Suppose the distance of P1 from the 5 into 10 to the power minus 8 coulomb is x meter. So distance of this point from this charge is 0.16 minus x meter. Okay. Now for the point P1 of zero potential, look at this, 5 into 10 to the power minus 8 divided by 4 pi epsilon naught into x plus minus 3 into 10 to the power minus 8 divided by 4 pi epsilon naught into 0.16 minus x. The sum of potential is 0. Okay. Look at this, from this relation, this is 5 by x, this equals to 3 divided by 0.16 minus x. Okay. So look at this is the 0.8 minus 5x and this equal to 3x. So 0.8 equal to 8x, therefore x equals to 0.1. So the position of zero potential obtained 0.x meter from the discharge. Now next we have to calculate the position of P2. Look at this, the position of zero potential P2 is y meter from this charge. So position of P2 from this charge is y minus 0.16 meter. Now we have to calculate the potential P2. So the potential at P2 is due to this charge is 5 into 10 to the power minus 8 divided by 4 pi epsilon naught into y plus minus 3 into 10 to the power minus 8 divided by y minus 0.16 into 4 pi epsilon naught, this equal to 0. So finally from this equation we get 5 by y, this equal to 3 divided by y minus 0.16. So this is the 5y minus 0.8 equal to 3y. So look at this, this is the 2y equal to 0.8. So y equal to 0.4. Therefore, distance of this point from this charge is 0.4 meter. Okay, next. Look at this. The 5 microcoulomb charges are placed each vertices of a regular hexagon of side 10 centimeter. We have to calculate the potential at the center of the regular hexagon. Now look at this. From each vertex, the distance of center is equal to side of it. If line drawn from here, look at this. Look at this angle 60 degree, this angle 60 degree. So this obviously 60 degree. So it forms an equilateral triangle. So this side equal to this side. So potential at the center of the regular hexagon, look at this, is the sum of potential of each charges. So there are 6 charges. Now charge is 5 into 10 to the power minus 6 divided by 4 pi epsilon naught, and this is the distance 10 centimeter, that is 0.1. Okay, so look at this, this is the 30 into 10 to the power minus 6 into 9 into 10 to the power 9 divided by 0.1. So this is the 300 into 9 into 10 to the power 3. So this is the 2.7 into 10 to the power 6 volt. Okay, understood? Now numerical number 2.12. 8 microcoulomb charges are placed at the origin. Now this charge is brought from P to R, then finally Q. We have to calculate work done. Now look at this, potential is not a path function, it is the state function. Look at this, work done from this to this, then this is equal to work done only from this to this. Okay, you know the potential difference is the work done to bring a charge from one point to another point. So work done to bring this charge is equal to Q into potential at the point Q minus potential at the point P. Okay, this is the required work done, delta W. Now look at this, therefore delta W is equal to, look at this, Q 2 minus 2 into 10 to the power minus 9, and this is the VQ. Look at this, Q divided by distance. So this is the 8 into 10 to the power minus 3 into 9 into 10 to the power 9 into 10 to the power 9 divided by, look at this, 4 into 10 to the power minus 2. And potential at P, look at this, this is the 8 into 10 to the power minus 3, 9 into 10 to the power 9 divided by distance. Distance is 3 into 10 to the power minus 2. Okay, now look at this, this is the minus 2 into 10 to the power minus 9. Now look at this, this is the 72. So this is the 72 into 10 to the power 6. And look at this, 10 to the power minus 2, 10 to the power minus 2. So this is the 10 to the power 2. This is the 1 by 4 by minus 1 by 3. Okay. Now look at this. Look at this. This is the minus 2 into 10 to the power minus 1. Look at this. 10 to the power 8, 10 to the power minus 9. So minus 1. Into 72 into look at this, minus 1 by 12. Okay, now this and this is the 6. So finally the work done equals to 1.2 joule. Okay, now look at this, this is a cube of side B. Now Q charge placed at each vertices of the cube. We have to calculate the electric intensity and potential E and V at the center of the cube. You know the intensity due to charge Q and Q at its midpoint is 0, and potential at this point is, look at this, V equal to 2q divided by 4 pi epsilon naught divided by this distance. If this distance is smaller, so this is the smaller. Okay, now look at this. The potential at the center of the cube is equal for each charges, and this equal to charge by distance of vertex, charge by distance of vertex from the center. Now the diagonal of the cube, is root 3 into b. So potential is 6 into potential due to one charge. So this is the 4 pi epsilon naught into root 3 into b. Okay. So this is the root 3 q divided by, so this is the root 3 q divided by 2 pi epsilon naught into b. Okay. No problem. Now intensity due to two diagonally opposite charges at the center is 0. So net electric field at the center becomes 0. So E equal to here 0. Okay, understood? Next, look at this. This is a dipole of charge minus q and q, and its dipole moment P equal to q into d directed along this direction. Now we have to calculate the potential at the point P due to this dipole. Here radius vector are Maxwell angle theta with the dipole moment small p. Now first of all, so look at this. So potential, suppose this is the point A, this is the point B. So potential at the point P is V equal to q divided by 4 pi epsilon naught into Bp plus minus q divided by 4 pi epsilon naught into AP. Okay. Now look at this. A perpendicular P is drawn from here. Suppose this is the A dash. Now another perpendicular drawn on produced. So this is the B dash. Okay. Now look at this. This is theta. Look at this is theta. So this is 90 minus theta. So this is the theta. If this is theta, look at this. So this is the d by 2 into cos theta. Look at this. This is the r. So this also r. So PV becomes r minus d by 2 cos theta. So look at this. Look at this. OP equal to r. So PB dash equal to r. So this is the, look at this. This is the r minus d by 2 cos theta. In the same way, look at this. This is the r. This is the d by 2 cos theta. So this is the, look at this, r plus d by 2 cos theta. Now here, so potential V equal to q divided by 4 pi epsilon naught. Look at this, Bp equal to r minus d by 2 cos theta. Okay, and plus minus q divided by 4 pi epsilon naught. This is the r plus d by 2 cos theta. Now take LCM. Look at this. Here V equal to q divided by 4 pi epsilon naught. Look at this. This is the r square minus d square by 4 cos square theta. And look at this. This minus this. So this is the 2 into d by 2 cos theta. Okay. Now q into d is equal to p. Therefore here p cos theta divided by 4 pi epsilon naught. This is the r square minus d square by 4 cos square theta. D square by 4 cos square theta. As d is negligible in comparison to r, so finally this equal to p cos theta divided by 4 pi epsilon naught r square. Therefore p vector dot r cube divided by 4 pi epsilon naught r square is the potential at P due to this dipole. So potential at P due to this dipole not only depends on distance of P from the dipole, it also depends on the angle made by r vector with the dipole moment P vector. Okay, understood? Look at this, a quadruple present here. We have to calculate potential at this point. Now look at this distance r and this is the A. Now look at this, the potential due to this charge, look at this is the Q divided by 4 pi epsilon naught, this is the R minus A. Now potential due to this and this charge, this becomes minus 2Q divided by 4 pi epsilon naught R, and potential due to this charge is equal to, look at this is the Q divided by 4 pi epsilon naught, this is the R plus A. Okay, so finally look at this Q by 4 pi epsilon naught, this becomes 1 by R minus A divided by 2 by R plus 1 by R plus A. Okay, now look at this is the Q divided by 4 pi epsilon naught, this is the R square minus A square into R whole divided by, look at this, from this result we get R square plus AR minus 2R square plus 2A square plus R square minus RA. Now look at this cancel out, this plus this 2R square and 2R square cancel out. So we finally get Q divided by 4 pi epsilon naught, this is the R square minus A square into R, and this is the 2A square. Now look at this, 2 into QA divided by 4 pi epsilon naught into R cube. So 2PA divided by 4 pi epsilon naught R cube. So look at this, electric field inversely proportional to 1 by R cube. So due to quadruple, intensity inversely proportional to cube of the distance. Due to dipole, it depends on 1 by square of the dipole, and due to monopole, that is single charge, Q equal to 4 pi epsilon naught by R, so V proportional to 1 by R. Understood? Next. Now electric potential energy. Electric potential energy is the amount of work done to bring an isolated charge from infinity to a point in the electric field. It is called potential energy. Suppose Q charge is here. A small Q charge is brought from infinity to this point. So potential energy of this charge at a distance r is equal to potential at this point into charge Q. So potential energy Q into potential at P. Okay. Therefore, this is the Q into capital Q divided by 4 pi epsilon naught R. So potential energy U equal to QQ by 4 pi epsilon naught R. Okay. Now you know the amount of work done to bring a charge from one point to another point is the difference of potential energy between the two charges. So work done delta W equals to U2 minus U1, that is Q1, that is QQ by 4 pi epsilon naught. This is the 1 by R2 minus 1 by R1. Okay. Now potential energy due to system of charges. Look at this. This is an equilateral triangle of side A. Now we have to calculate that potential energy of the system of charge Q1, Q2, Q3. So look at this, the potential energy due to this and this charge is Q1, Q2 divided by 4 pi epsilon naught into side of the equilateral triangle is A. Okay. Now look at this, the potential energy between this and this. Look at this is the Q2, Q3 divided by 4 pi epsilon naught A. Now this is the Q3, Q1. So Q3, Q1 divided by 4 pi epsilon naught into A is the total potential energy of the system. Okay. Now next. Now look at this, charge Q1, Q2, Q3, Q4 are placed at the vertices of a square of side A. Now we have to calculate the potential energy of the system. Now, first of all, the potential energy between this and this charge. Look at this. This is the Q1, Q2 by 4 pi epsilon naught A. Now, potential energy due to this and this. So, this becomes Q1, Q3 divided by 4 pi epsilon naught this distance. This distance is the root 3 into A. Sorry, this distance is the root 2 into A. Now, potential energy between this and this. So, this is the Q1, Q4 divided by 4 pi epsilon naught into A. Now, potential energy between this and this. So, this is the Q2, Q3 divided by 4 pi epsilon naught into A. Look at this, the potential energy between this and this. So, this is the Q2, Q4 divided by 4 pi epsilon naught root 2 into A. Now, potential energy between this and this. So, this is the Q3, Q4 divided by 4 pi epsilon naught into A. Okay, understood? Now, next. Now, equipotential surface. Look at this. Suppose this is a surface. If potential at every point on this surface is equal, then it is known as equipotential surface. Now you know the amount of work done to bring a charge from one point to another point is equal to delta W equal to Q into V2 minus V1, as potential at all points of its surface is equal. So work done, this becomes V minus V. So this is the 0. Okay. If work done to bring a charge from one point to another point is 0, so look at this, E vector dot dr vector, this equal to 0. Therefore E vector and dr vector are perpendicular to each other. Therefore, electric field always perpendicular to the equipotential surface. Therefore, the characteristics of equipotential surface: number 1, the work done to bring a charge from one point to another point is 0, and electric field is normal to the equipotential surface. And finally, the two equipotential surfaces never intersect each other. Okay, now we draw some equipotential surfaces. Look at this. This is a point charge Q. If we draw the concentric sphere about the charge Q, then all the surface of concentric sphere will be the equipotential surface. Look at this. This is the V1, this is the V2, this is the V3. Okay, this is the equipotential surface. This also equipotential surface. This also equipotential surface. And electric field, look at this, is directed normal to the equipotential surface. Look at this. This is the direction of electric field. Understood? Next, look at this. If the electric lines of force are equidistant and parallel, so they represent the uniform electric field. Now, all the surfaces normal to the electric field are the equipotential surface. So look at this. This is the equipotential surface. Now look at this. This also the equipotential surface. Now look at this. This is the equipotential surface. This is the equipotential surface. Okay. Now we have to express the relation between electric intensity and electric potential. Look at this. This is an uniform electric field. Now there are 2 points, point P and point Q, are separated by a very small distance dr. Okay. The potential at the point P is V and the point Q is V minus dV, because potential decreases in the direction of lines of force. Okay, now look at this. The amount of work done to bring an isolated unit positive charge from Q to P is minus E into dr, because electric field directed along this direction but displacement along this direction. Now this work done is equal to potential difference between this point and this point. So this is equal to V minus dV. That is minus E into dr is equal to dV. Therefore, E equal to minus dV by dr. Therefore, electric field is the negative gradient of potential. In vector form, it can be expressed as E vector is equal to Ex I cap plus Ey j cap plus Ez k cap. So this becomes minus del V by del X I cap minus del V by del Y j cap minus del V by del Z k cap. Okay. Now from this relation there are another important relation can be derived. Look at this. Here dV is equal to minus E into dr. Therefore look at this. Now integration of dV equal to integration of E into dr. So look at this. Suppose this is the VA and this is the VB. Suppose this is the RA and this is the RB. So look at this. This is the VB minus VA is equal to minus integration of RA to RB. This is the E into dr. Okay. This is another important relation to obtain potential in a given point where intensity E is given. Okay. Now there are three important relations. This and this are obtained. Now to clarify this expression, we have to solve three equations. Okay. Here V equal to 3x minus x cube. Find the points where electric intensity is 0. We know the electric intensity is the negative gradient of potential. Look at this. Here variable is x. So E equal to minus dV by dx. Therefore, we can get, look at this, this is the 3 into 1 minus 3x square. As intensity is 0, so this side will be 0. Now, look at this, this is the 3x square equal to 3. So, x square is equal to 1. Therefore, x equals to plus minus 1. Therefore, at x equals to 1 and x equals to minus 1, electric intensity becomes 0. Okay. Now next. Now look at this. V equal to 3xyz. We have to calculate intensity at the point 1, 1, 1. Now we know, look at this. E vector is equal to negative sign of del V by del X I cap. Here del V by del Y j cap. And here del V by del Z k cap. Okay. Now look at this. Now here del V by del X. So here del of 3xyz by del X. Look at this. Here only X variable, YZ constant. So look at this. This becomes 3yz. Now y equal to 1 and z equal to minus 1. So this is the 3, 1, minus 1. So this is the minus 3. Now in the same way, del v by del y, this will be 3xz. Now x plus z minus 1. So this is the also minus 3. Now del v by del z, look at this. Here z variable. If z variable, so differentiation of z with respect to z1, so this is the 3xy. Now here x1, y1, so this is the 3. Therefore, now look at this E vector equal to minus del v by del x I cap. So this is minus into minus 3 I cap. Now minus del v by del y. So this is the minus 3 j cap and this is the minus 3 k cap. Okay. Therefore, look at this. This is the 3 I cap plus 3 j cap minus 3 k cap. Therefore, magnitude of E vector is equal to 3 root 3 volt per meter. Okay. Understood? Now next, look at this. Find potential inside a solid insulating sphere. Now look at this. Suppose this is a insulating sphere. Now we have to calculate the potential at a distance smaller from the center of the insulating sphere. We know the intensity inside the insulating sphere E equal to, look at this, Q divided by 4 pi epsilon naught r cube into small r. Now E is given. Now from relation, look at this. This is the, suppose this point P and surface, suppose this point is Q. The potential at P is equal minus potential at Q is equal to integration of E into dr from, look at this point initial point, so this is the r, and this point is the final point, so this is the smaller. Now put the value of E here. So look at this, Vp minus, what is the value of Vq? Vq is the potential on the surface of a insulating sphere, and this is equal to Q divided by 4 pi epsilon naught capital R. So this is the Q divided by 4 pi epsilon naught capital R equal to, look at this is the negative sign of, look at this is the Q by 4 pi epsilon naught r cube small r dr integration capital R to small r. Now look at this is the Vp minus Q divided by 4 pi epsilon naught capital R. Now what is the integration of it? R dr is the integration is r square by 2. So look at this, minus Q divided by, this is the r cube, sorry, 4 pi epsilon naught, this is the r cube and this is the r square by 2, limiting value is smaller to capital R. Now this is equal to, look at this is the cube, this is the r square minus capital R square divided by negative sign of, look at this is the 8 pi epsilon naught, this is the r cube. Okay, here Vp equal to Q by 4 pi epsilon naught r, and this is the, look at this is the negative sign, sorry, this is the negative sign, so this is the Q divided by r square minus r square by 8 pi epsilon naught r cube. So look at this, the denominator is 8 pi epsilon naught r cube, and this is the, look at this is the r square, look, sorry, this is the 2r square minus r square minus plus r square. So look at this, Q into, look at this is the 2r square minus r square plus r square. Okay, so finally Vp equal to, look at this, Q divided by 8 pi epsilon naught r cube, and this is the 3r square minus r square. Okay, understood? Now next, look at this. Suppose these two conductor, one is given positive charge and another is given negative charge, constitute a capacitor. This plate is called positive plate of the capacitor and this plate is called negative plate of the capacitor. Now potential of this plate is positive and potential of this plate is negative. The potential of the positive plate is called potential difference between the two plates of the capacitor or potential of the capacitor. Now if Q be the charge given here, so this is also minus Q. The charge given to the plate is directly proportional to the increase of potential. Therefore, look at this, Q equal to C into V. C is called capacitance of the capacitor. Now, if, look at this, if V equal to 1, then C equal to Q. Therefore, capacitance of a capacitor is numerically equal to charge given to it to increase the potential by unity. Okay, look at this, the capacitance of capacitor depends on shape and size of the conductors, geometrical placing of the conductors and medium between the two conductors. Okay, look at this, if a graph is plotted between, look at this is the C and this is the Q, so this graph becomes straight line passing through origin. Now if a graph is plotted between, look at this is the V and this is the C where Q constant, so this graph is a rectangular hyperbola. Okay, now we have to calculate the capacitance of a sphere. Look at this. Suppose q charge given to a sphere of radius r. So potential on its surface V equal to q by 4 pi epsilon naught r. So this is the q by 4 pi epsilon naught r. Now what is the c? Look at this. You know q equal to cv. So c equal to q by v. If you put the value v, what will be the value obtained? Now look at this. This is the q divided by 4 pi epsilon naught r. So c equal to 4 pi epsilon naught. This is the r. Therefore, capacitance of a sphere is directly proportional to the radius of it. In CGS system, look at this, 4 pi epsilon naught equal to 1. So in CGS system, capacitance is numerically equal to radius of a sphere. Understood? Next. Suppose this is a parallel plate capacitor. Two plates. One plate has charge plus Q, other plate has charge minus Q. The negative plate is earth. And now area of each plate is capital A. So surface density of this plate is sigma equal to Q by epsilon naught. And here sigma equal to minus Q by epsilon naught. Now if we draw the lines of force here, look at this. The lines of force becomes parallel to each other. Okay. So electric field between the two plates are uniform in magnitude and directed from positive plate to negative plate. What is the electric field? Look at this. Due to positive plate, this is the sigma by 2 epsilon naught, and this is, and due to negative plate also sigma by 2 epsilon naught, and these two electric field directed from upper plate to lower plate. Now look at this. This becomes sigma by epsilon naught, that is q by epsilon naught into a. Okay, no problem. Now look at this, amount of work done to bring an isolated unit positive charge from this point to this point is the potential difference. So potential difference V is the work done. So work done equals to force for unit charge into displacement. So V equal to Q into D divided by epsilon naught into A. Now V is obtained. So what is the capacitance? Capacitance is equal to Q by V. So C equal to Q by V. This is the Q divided by QD divided by epsilon naught A. So C equal to, this is the epsilon naught A by D is the capacitance between the two plates of a parallel plate capacitor. Okay. Look at this, a number of parallel plates placed are side by side and two alternate plates are connected to the positive terminal and other plates are connected to the negative terminal. Then the capacitance becomes, this is the minus and this is the plus. Look at this, the distribution of charge. Look at this, this is the plus. Look at this, this is the minus, 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 minus. This is the minus, minus, minus. Okay, this is the plus. Okay, this is the plus. This is the minus, 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 minus. This is the plus. Okay, look at this. This is the plus. Okay, and this is the minus, minus, minus. Okay, look at this. In this case, the capacitance of the combination, this becomes C equal to n minus 1 epsilon naught A by D. Now look at this. Look at this. Two plates form a capacitor. Now this three plate forms two capacitor. Now these four plates forms 1, 2, 3. So number of capacitor becomes n minus 1 epsilon naught A by D. Okay, understood? Next. Now look at this. This is a parallel plate capacitor. Its capacitance C equal to epsilon naught A by D. Now if a dielectric slab of constant K is introduced between the space between the two plates, then capacitor becomes C dash equals to K into C. So this becomes K epsilon naught A divided by D. Okay, understood? Now a NCERT numerical. Now look at this. This is a parallel plate capacitor of capacitance 8 picofarad. What will be the capacitance if distance between the two plates reduced to half of the present case? Now look at this. Here C equal to epsilon naught A by D is the capacitance of this capacitor. Now this is the 8. So 8 picofarad is equal to epsilon naught A by D. Now we have to calculate capacitance of it. What will be the capacitance of it? Now this is the C1. So epsilon naught A divided by this distance is the key D by 2. This distance is D by 2. So this is the D by 2. So this becomes 2 into epsilon naught A by D. So this equals to 2 into 8. So this is the 16 picofarad. Now what is the capacitance of it? Here capacitance C2 equal to K epsilon naught A by D. Look at this. This is the K. Epsilon naught D is equal to 8 picofarad. So this is the 8. Now K equal to 6. 6 into 8. So this is the 48 picofarad. Okay. Understood? Next. Now look at this. Sum number 2.8. A parallel plate air capacitor has area A equal to 6 into 10 to the power minus 3 meter square, and distance between the two plates is 3 into 10 to the power minus 3 meter. Find the capacitance. If this capacitor is connected to a 100-volt potential difference, find the charges on each plate. Okay. Now first of all, the capacitance of air capacitor C equal to epsilon naught A by D. Now look at this. Here epsilon equal to 8.85 into 10 to the power minus 12. This is the 6 into 10 to the power minus 3, and this is the 3 into 10 to the power minus 3 farad. Now look at this. So this becomes, look at this and this cancel out. So this becomes 17.7 picofarad. Okay. Now what is the charge on positive plate and negative plate when potential difference of 100 volt are kept between the two plates? Now look at this. So Q charges, Q equal to C into V. So this is the 17.7 and this is the 100. This is the picocoulomb. So this is the 1770 picocoulomb. Therefore 1.77 nanocoulomb is the charge at the positive plate and minus 1.77 nanocoulomb charge at the negative plate. Understood? Next. Now in question 2.9, if a dielectric slab of constant K equal to 6 is introduced between the two plates, what will be the charge? Now when a dielectric slab of dielectric constant 6 is introduced in it, the capacitance C dash becomes K into C. Now this is the 17.7 picocoulomb. So this is the 6 into 17.7 picocoulomb. So charge on each plate Q dash is equal to C dash into V, where C dash is equal to 6 into 17.7 into 100 picocoulomb. Now C dash equals to 6 into 1.77 picofarad. So Q dash equals to C dash B. So 6 into 1.77 into 100. This is the picocoulomb. And now this is the 6 into 1.77 nanocoulomb. So this is the 10.62 nanocoulomb. Okay. Now look at this. If battery is disconnected and dielectric slab introduced between the two plates, the charge remains same as usual, that is 1.77 nanocoulomb. Therefore there is very important concept. If battery is connected between the two plates of a capacitor and a dielectric slab introduced in it, its potential constant, so charge increased K times. But if battery is disconnected and dielectric slab is introduced in it, its charge remains constant, therefore potential decreases. Okay, remember it. Okay, look at this. This is the parallel plate air capacitor of capacitance 2 farad. The separation between the two plates is 0.5 centimeter. You have to calculate the area of each plate. Now look at this. Here C equal to epsilon naught A divided by D. Now C equal to 2 farad, and this is the 8.85 into 10 to the power minus 12, and this is the A, and this is the 0.5 into 10 to the power minus 2. So A becomes, look at this, 0.5 into 2, that is 1, 10 to the power minus 2. So this is the 10 to the power 12 into 10 to the power minus 2 divided by 8.85. So look at this is the 10 to the power 10 divided by 8.85 meter square. So look at this, if it expressed in the kilometer square, it should be divided by 10 to the power 6. So this becomes 10 to the power 4 by 8.85. This is the kilometer square. So area of the plate becomes very large. Okay, look at this. A parallel plate capacitor is to be designed such that voltage rating is 10 to the power 3 volt, and dielectric slab introduced in the capacitor is 3. The maximum breakdown field is 10 to the power 7 volt per meter. If we use 10% of this field and we make a capacitor of capacitance 50 picofarad, find the area of each plate. Now first of all, what is the relation between E dash and V? You know V equal to E dash into D. Okay, so look at this, this is the 10 to the power 3 and this is the 10 to the power 6 into D. So look at this, D is equal to 10 to the power minus 3. Therefore capacitance C is equal to K epsilon naught A by D. Now look at this, here C, K, D and epsilon naught are given. We have to calculate A. Now look at this, this is the 50 picofarad, that is 50 into 10 to the power minus 12, K equal to 3, this is the 8.85 into 10 to the power minus 12 into A divided by 10 to the power minus 3. Okay, now look at this. Now look at this and this cancel out. So A become, look at this, A become 50 into 10 to the power minus 3. This into this equals to 26.25. So look at this, the area of each plate is almost 2 into 10 to the power minus 3. So area of the plate is 2 into 10 to the power minus 3 meter square. Okay, next. Now look at this. There are two concentric spherical shells of radius R1 and R2. Look at this, Q charge is given to the inner spherical shell and outer spherical shell is earthed. Now look at this, due to induction of charges, the charge in the inner surface of this plate is negative. Okay, therefore the potential difference between the two plates V is equal to, look at this is the Q divided by 4 pi epsilon naught R1 plus minus Q divided by 4 pi epsilon naught into R2. Okay, this is the Q divided by 4 pi epsilon naught. This is the 1 by R1 minus 1 by R2. Now this is Q, this is the R2 minus R1 and this is the 4 pi epsilon naught R1 R2. Now potential is obtained. So what is the capacitance? Capacitance C equal to Q by V. Q is the, look at this Q. So capacitance C is equal to Q by V. Now this is the 4 pi epsilon naught R1 R2 divided by R2 minus R1. Okay, no problem. Now look at this, if R1 almost equal to R2, okay, and R2 minus R1 is equal to small d, then look at this, C becomes 4 pi epsilon naught, this is the R1 square divided by d. Now 4 pi R1 square is equal to capital A. So look at this is the epsilon naught A by D, just like the capacitance of a parallel plate capacitor. Okay, now look at this, if R2 greater than R1, okay, Now C equal to 4 pi epsilon naught R1, and this is the 1 minus R1 by R2. Now R1 by R2 tends to 0 because R2 greater than R1. So look at this. This is the 4 pi epsilon naught R1. This is the capacitance of a sphere of radius R1. Okay. Understood? Next. Now look at this. There are two concentric spherical shell of radius R1 and R2. Now the inner spherical shell is Earth and Q charge given to the outer spherical shell. Suppose induced charge in the inner spherical shell be Q dash. As it is Earth, so its potential V equal to 0. Now 0 equal to, look at this, the potential due to charge Q dash. So this is the Q dash by 4 pi epsilon naught R1, and potential due to Q. So this is the Q divided by 4 pi epsilon naught. This is the R2. So from here Q dash is equal to Q R1 by R2 with negative sign. Now what is the potential difference between these two spherical cells? Look at this, the potential difference V dash. This becomes Q plus Q dash divided by 4 pi epsilon naught. This is the R2. Now look at this, Q plus Q dash. So this is the Q minus Q R1 by R2 divided by 4 pi epsilon naught. This is the R2. So look at this Q. This is the R2 minus R1 divided by 4 pi epsilon naught R2 square. Therefore C equal to Q by V dash is equal to 4 pi epsilon naught R2 square by R2 minus R1 is the capacitance of the combination when inner spherical shell is Earth and outer is charged with Q. Okay, understood? Now next, capacitance of a cylindrical capacitor. Look at this, R1 and R2 with the radius of two concentric cylinder. Now look at this, the outer cylinder is Earth and Q charge is given to the inner cylinder. Now P be a point at a distance r from the common axis of the cylinders. So look at this, if E be the electric field at the P, so E into, now look at this, 2 pi r into L, this equals to charge enclosed by the Gaussian surface. So this is the Q by epsilon naught. Q divided by 4 pi epsilon naught RL. Now we have to calculate the potential difference between this and this. So look at this, if this is the potential V1 and this is the potential V2, so look at this, V1 minus V2, this equal to integration of E vector dot dr. Now look at this, V2 is the initial, so this is the R2. Okay, V1 is the final potential, so V1 is equal to here corresponding to R1. Now look at this here, V1 minus 0, this is the, look at this, Q divided by 4 pi epsilon naught L, and this is the dr divided by R, this is the R1 and this is the R2. So look at this is the Q divided by 4 pi epsilon naught L into ln R2 by R1. Okay, so this is the potential difference between the two concentric cylinder. Therefore capacitance C equal to Q by V. So Q by this. So this is the 4 pi epsilon naught L divided by ln R2 by R1. Okay, understood? Look at this. There are two concentric spherical shell of radius 12 centimeter and 13 centimeter. Now we have to calculate capacitance. Now C equal to 4 pi epsilon naught, this is the R2 R1 divided by R2 minus R1, and K is the dielectric constant. Now capacitance C equal to 4 pi epsilon naught K R1 R2 by R2 minus R1. Look at this, here R2 is equal to, here R2 equals to 13 into 10 to the power minus 2 meter. R1 is equal to 12 into 10 to the power minus 2 meter. 10 to the power minus 2 meter. And K is equal to this. So C equal to, look at this, C equal to, this is the 1 by 9 into 10 to the power 9, and this is the, look at this, 32 into 12 into 13 into 10 to the power minus 4, and this divided by 13 minus 12, that is 1 into 10 to the power minus 2. So finally we get, look at this, this is the 32 into 12 into 0.13 divided by 9 into 10 to the power 9 farad. Okay, so this is the 5.54 into 10 to the power minus 9 farad. So this is the 5.54, this is the nanofarad. Okay, now we have to calculate potential of the inner sphere. So look at this, V equals to charge by capacitance, so charge Q by C. Now look at this, this is the 2.2 into 10 to the power minus 6 coulomb, and this is the 5.54 into 10 to the power minus 9 farad. Therefore this is the 4.5 volt. Okay, so this is the 4.5 volt. Okay, next. Now we have to calculate the ratio between the capacitance of isolated sphere of radius 12 centimeter and this combination. Look at this, here C equal to 4 pi epsilon naught K R1 R2 by R2 minus R1. Now C dash equals to 4 pi epsilon naught, this is the R1. So look at this, C by C dash, look at this, C by C dash, so this is the K R2 divided by R2 minus R1, R2 minus R1. Now this is the 32, and this is the 13 into 10 to the power minus 2, and this is the 1 into 10 to the power minus 2. So the capacitance becomes 32 into 13 times. Okay, so this is the 416 times the capacitance of an isolated sphere. Okay, next, look at this, the capacitors of capacitance C1, C2, C3 are connected in series across a potential difference V. So charge here, this is the, suppose this charge is Q. So due to induction, charge here also Q. Now look at this, this charge is also Q, because the positive charge given this side, this positive charge here. So here charge on each capacitor becomes same. Okay, so look at this, the potential difference between the two plates of the capacitor, V1 becomes Q by C1, V2 becomes, this is the Q by C2, and V3 becomes, this is the Q by C3. So total potential V equal to, this is the V1 plus V2 plus V3. Therefore this is the Q, this is the 1 by C1 plus 1 by C2 plus 1 by C3. Okay, understood? If C be the equivalent capacitance of the combination, then look at this, V equal to Q by C. So from here Q by C is equal to Q into 1 by C1 plus 1 by C2 plus 1 by C3. Now this is cancel out. So this is the 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now look at this, 1 by C greater than 1 by C1, therefore C less than C1. 1 by C is also greater than 1 by C2, therefore C less than C2. And finally 1 by C greater than 1 by C3, so C less than C3. Therefore equivalent capacitance C in series combination is smaller than smallest capacitance of the combination. Okay, now look at this, the capacitance C1, C2, C3 are connected in parallel across a potential difference V. Suppose charge here is Q1. Okay, this charge Q1. Charge here is also Q2. Charge here is Q2. And charge here is Q3. Okay. Now, so total charge conducted from the battery Q is equal to, look at this, Q1 plus Q2 plus Q3. Okay, look at this, as all are connected across V, so potential of each capacitor is V. So look at this, Q1 becomes C1 into V, Q2 becomes C2 into V, and Q3 becomes C3 into V. So this is the Q. Now if equivalent capacitance is C, then Q equal to CV. So look at this, CV equal to C1V plus C2V plus C3V. So C equal to, look at this, C1 plus C2 plus C3. Okay. So equivalent capacitance is algebraic sum of capacitance of the combination. Okay. Now next. Now look at this. Three capacitors, each of capacitance 9 picofarad, are connected in series across a potential difference of 120 volt. We have to calculate the potential across the each capacitor, charge stored in each capacitor, and equivalent capacitance. Now first of all, equivalent capacitance. We know in series combination 1 by equivalent capacitance equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is the 1 by 9 plus 1 by 9 plus 1 by 9. So look at this, this is the 3 by 9. So this is the 1 by 3. So C equal to 3 picofarad. Okay. Now total charge stored in each capacitor. So look at this, Q equal to C into V. So this is the 3 picofarad into 120 volt. So 120 volt. So this is the 360 picocoulomb. Now V1 equal to V2 equal to V3. So this is the Q by C1. So this is the 360 picocoulomb divided by 9 picofarad. Okay, so look at this, this is the 40 volt. Okay, understood? Now next. Now look at this, 2 picofarad, 3 picofarad and 4 picofarad are connected in parallel across a 100 volt PD. Now we have to calculate equivalent capacitance and charge stored in each capacitor. Now first of all, look at this. So equivalent capacitance C equal to C1 plus C2 plus C3 in parallel combination. So this is the 2 plus 3 plus 4. So look at this, this is the 9 picofarad. So the equivalent capacitance is 9 picofarad. Now charge in the first capacitor, Q1 equal to C1 into V. So this is the 2 into 100. So this is the 200 picocoulomb. Okay. Now next, Q2 is equal to C2 into V. So this is a 3 into 100. So this is the 300 picocoulomb. And finally Q3 is equal to C3 into V. So this is the 4 into 100. So this is the 400 picocoulomb. Okay. Understood? Now next. Now an electrician required 2 microfarad capacitor at 100 kilovolt. Now 1 microfarad capacitor which is working at 400 volt is available. What number of capacitor requires to achieve this? Now first of all, we have to obtain the voltage. Now look at this, if we add 1 microfarad capacitor in series, then look at this, this is the 400 volt, this is the 400 volt, this is the 400 volt. So this is the 1200 volt. So requirement is 1000 volt, but final obtained is 1200 volt. So this is possible. Now to gain the potential difference of 1200 volt, the equivalent capacitance decreases to 1 by 3 because in series combination of 1 microfarad capacitor, equivalent capacitance becomes 1/3. Now we have to require 2 microfarad capacitor. So number of branches required 2 by 1 by 3. So this is the 6. So 6 number of these lines are required to achieve this. So look at this, the combinations are, look at this. This is the 2, okay. Now this is the 3. Now this is the 4. This is the 5. Okay. And this is the 6. So total number of, look at this, capacitor required to achieve 2 microfarad 1 kilovolt is equal to, look at this, 18. 1, 2, 3 into 6, 18. Okay. So 18 number of capacitors required to achieve this. Okay. And combinations are such. Okay. Now look at this. This is the 100 picofarad. 100 picofarad, 200 picofarad, 200 picofarad are connected in such a way with 300 volt PD. We have to calculate potential difference across each capacitor and charge stored in each. Now look at this. Equivalent capacitance, look at this. This is the equivalent capacitance. Look at this. C2 and C3 are in series. As C2 and C3 are in series, so equivalent capacitance between C2 and C3 is C2 into C3 divided by C2 plus C3. So this is the 200 into 200 by 200 plus 200. So this is the 100 picofarad. Okay. Now this 100 and this 100 are in parallel. So equivalent capacitance is 200 picofarad. Now 200 picofarad and 100 picofarad are in series. So equivalent capacitance is, look at this. This is the 200 into 100 divided by 200 plus 100. So this is the 200 by 3 picofarad. Now total charge supplied by the battery Q equal to C into V. So this is the 300 volt into 200 by 3 picocoulomb. So this is the 2 into 10 to the power 4 picocoulomb. Okay. Now look at this. The combination, look at this. This is the, look at this. This is the 100 picofarad. This is the, look at this. This is the 100 picofarad. Okay. Look at this. This is the also 100 picofarad. Okay. This is the C1 and this is the C4. And finally, this is the 200, this is the 200, and this is the C2 and this is the C3, and now this is the A and this is the B. Suppose this is the A and this is the B, and VAB is equal to 300 volt. Okay. Now look at this. The charge stored here, look at this. The charge stored here is this. So Q4 is equal to 2 into 10 to the power 4 picocoulomb. Now V4 is the Q4 by C4. So look at this. This is the, look at this. This is the 2 into 10 to the power 4 by 100. So this is the 200 volt. Okay. Now look at this. So potential difference between this and these two is obviously 100 volt. Because look at this, total potential difference between A and B is 300 volt. Here A and this point, suppose D point is the 200 volt. So between this and this is the 100 volt. So PD across C, so V1 is equal to 100 volt. Now what is the charge in it? Look at this, the charge Q1 is equal to 100 into V. So this is the 1 into 10. So this is the 1 into 10 to the power 4 picocoulomb. Now look at this. What is the potential difference? Look at this. Here potential difference between this point and this point is 100 volt. So potential across this is 50 volt and across this is 50 volt because they are connected in series. If this is the 50 volt PD, so look at this charge here. Look at this. This is the 200 into 50. So charge here is 50 volt into 200. So this is the 1 into 10 to the power 4 picocoulomb. Okay, understood? So final result is, look at this. This is the 200 volt. Now charge in it 2 into 10 to the power 4 picocoulomb. Here this is the 100 volt. Charge here is, look at this, 1 into 10 to the power 4 picocoulomb. This is the 50 volt, this is the 50 volt, and charge in each is 1 into 10 to the power 4 picocoulomb. Okay, understood? Now next. Now energy stored in a capacitor. Now look at this. Suppose this is a capacitor. Its capacitance is C. Now Q charge given to it. So now Q charge given to it. So its potential V equal to Q by C. Now amount of work done to increase its charge from Q to Q plus dQ is dW is equal to V into dQ. Now V equal to Q by C into dQ. So total energy U equal to, so total energy U equal to integration of 1 by C Q dQ from 0 to Q. So this is the 1 by C, this is the Q square by 2. So Q square by 2 is the energy stored in it. Now Q equal to C square V square. Now Q square equal to C square V square divided by 2C. So the energy stored is half CV square. Now if this capacitor is charged by a battery of potential difference V, so energy supplied by the battery is Q into V. Now Q equal to CV, so CV into V, so CV square. So energy supplied by the battery is CV square. Energy stored in the capacitor is half CV square. So energy dissipated as heat is CV square minus half CV square. So this is the half CV square. So energy stored is equal to energy dissipated is equal to half of energy supplied by the battery. Okay, now next. Now look at these two conductors. The charge in it is Q1 and capacitance C1. Now charge in it is Q2 and capacitance C2. Now potential in it V1 is equal to Q1 by C1 and potential in it is Q2 by C2. If a conducting wire is connected between the two conductors, then charge flow from the higher potential to lower potential. Suppose first is the higher potential, second is the lower potential. So charge flow from this to this, and finally a common potential is reached. If V be the common potential, then final charge in it Q1 equal to C1 into V and final charge in it Q2 equal to C2 into V. So from conservation of charge, final charge equal to initial charge. Now look at this. So this is the Q1 plus Q2 equal to capital Q1 plus capital Q2. So this is the C1V plus C2V. This is C1V1 plus C2V2. Now V equal to, this is the C1V1 plus C2V2 divided by C1 plus C2. So look at this. Now C1V1 equals to Q1 plus Q2 by C1 plus C2. So common potential V equal to total charge by total capacitance. Now during connection between the two conductors, electrical sparking takes place. Electrical sparking associated with heat energy, light energy and sound energy. So some electrical energy is dissipated. Now dissipation of energy is equal to initial energy minus final energy. So this is the initial energy and this now initial energy minus final energy. Look at this. This is the dissipation of energy. Now if we put the value of V equal to C1V1 plus C2V2 by C1 plus C2, then we can get look at this, half C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. This is the expression of dissipation of energy. Okay. Now next, look at this. A capacitor of capacitance 600 picofarad is charged with a 200 volt potential difference. Now the battery is disconnected. Now it is connected to an uncharged capacitor of capacitance 600 picofarad. Find the dissipation of energy. Now look at this, the dissipation of energy W equal to half C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. Look at this, put the value of C1 C2 V1 V2. So look at this, this is the half into 600 into 600 divided by 600 plus 600, and this is the 200 minus 0 whole square. So look at this, this is the half into, this is the 300, okay, and this is the 4000 picojoule. Now look at this, this is the 2 and 6, so this is the 6 into 10 to the power 6 picojoule, so this is the 6 microjoule. Okay, understood? Now next, now look at this, a capacitor of capacitance 4 microfarad is charged with 200 volt potential difference. Now it is connected to an uncharged capacitor or 2 microfarad capacitors. Now what is the loss of energy? Now loss of energy delta W equal to half C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. Now this is the half, this is the 4 into 2 divided by 4 plus 2, and this is the 200 whole square. Okay, now look at this, this is the 4 by 6 into 200, that is 400, this is the microjoule. Okay, now look at this, this is the 2 and this is the 3, so 8, that is 2.67 into 10 to the power 4 microjoule is the dissipation of energy from the first capacitor. Okay, now next, look at this, a parallel plate capacitor having charge at the positive plate is Q and charge at the negative plate is minus Q. And look at this, the distance of separation is D and area of each plate is capital A. Now the electric field on the negative plate due to Q charge is E1 equal to, look at this, Q divided by 2 epsilon naught A. And this electric field directed along this direction, this is the E1. Now the force on the negative plate due to this electric field is F equal to minus Q into E1, that is minus Q square by 2 epsilon naught A. So look at this, electric field directed along this direction, so force experienced by the negative charge is directed along this direction. So the force of attraction between the two plates of a parallel plate capacitor is F equal to, this is the Q square by 2 epsilon naught A. This is the magnitude of force of attraction. Now amount of work done to displace the negative plate by a distance delta x is delta W equal to F into delta x. Okay, so this is the, look at this, Q into delta x divided by 2 epsilon naught A. Okay, Q square into delta x by 2 epsilon naught A. Now look at this, the energy stored per unit volume U equal to delta W by, look at this, volume A into delta x. So look at this, now this is the Q square delta x by 2 epsilon naught A into A delta x. Now energy density Q square by A square into half of epsilon naught. Now look at this. This is the half epsilon naught Q epsilon naught A whole square. Now Q epsilon naught is the electric field between the two plates of a parallel plate capacitor. If E be the electric field between the two plates of the parallel plate capacitor, then energy density U is equal to half epsilon naught E square. Okay, understood? Now next. Now this is a parallel plate capacitor having area of each plate is 90 centimeter square. Distance of separation between the two plates is 2.5 millimeter. It is connected to a 400 volt supply. What is the energy stored in it and the energy density stored in it? Now look at this. The capacitance C equal to, look at this, the capacitance C equal to epsilon naught A divided by D. So this is the 8.85 into 10 to the power minus 12, and this is the 90 into 10 to the power minus 4, and D is equal to 2.5 into 10 to the power minus 3 is the farad. So this is, look at this, this is the 8.85 into 9 divided by 2.5, this is the picofarad. Now energy stored U is equal to, look at this, half CV square. Now this is the half, C is the 8.85, this is the 2.5 into 9 into, look at this, V equal to 400 volt whole square. So this is the picojoule. Okay. Now the calculation is, look at this, this is the 16. So finally we get half into 8.85 divided by 2.5 into 9 into 16 into 10 to the power 4 picojoule. Okay. This is the 2.548 into 10 to the power minus 6 joule. Okay. So finally we get 2.55 into 10 to the power minus 6 joule. Okay. Now energy density here. Now energy density U is equal to, look at this, half epsilon naught E square, where E is the electric field. Now V is the potential difference between the two plates, D is the 1.5 millimeter. So electric field is equal to V by D. Now look at this, here V equal to 400 and D equal to 2.5 into 10 to the power minus 3. So finally we get 1.6 into 10 to the power 5 volt per meter. Therefore energy density small u equal to half epsilon naught. So this is the 8.85 into 10 to the power minus 12 into E square. Look at this, E is the 1.6 into 10 to the power 5 whole square. So look at this, finally we get 4.42 into 10 to the power minus 12, and this is the 2.56 into 10 to the power 10. Okay. So this is the 4.42, this is the 2.56 into 10 to the power minus 2 joule per meter cube. This is the 0.11 joule per meter cube is the energy density between the two plates of a parallel plates capacitor. Okay. Next, look at this. This is a parallel plate capacitor. The charge at the positive plate is Q and charge at the negative plate is minus Q. When a dielectric slab of constant K is introduced between the two plates, a dielectric polarization takes place. Look at this here. This is the negative positive. 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 Okay. Look at this. So look at this. A dielectric polarization takes place within the dielectric material. So look at this. The negative polarizing charge is produced at this side and positive charge produced this side. The magnitude of polarizing charge is, look at this, QP and minus QP. Now electric field due to Q and minus Q is directed along this direction. So the net electric field, look at this, the net electric field is original electric field E naught minus electric field due to polarizing charge QP and minus QP. Look at this, because the polarizing charge produces electric field EP along this direction and original electric field E naught along this direction. So this is the net electric field E. We know when a dielectric slab is placed between the two plates of a parallel plate capacitor, the electric field Q equal to K epsilon naught A. Now due to original charge Q and minus Q, electric field is Q epsilon naught A, and due to polarizing charge, this is the QP divided by epsilon naught A. So finally we get Q by K equal to Q minus QP. So look at this, the polarizing charge Q equal to 1 minus 1 by QP equal to 1 minus 1 by K. Understood? Next. Now look at this. This is the two concentric cell of charge Q1 and Q2 and radius R1 and R2. Now the potential at this point due to charge Q1 and Q2 is V1 equal to Q1 by 4 pi epsilon naught R1 plus Q2 divided by 4 pi epsilon naught R2. Now potential V2 at this point is equal to V2 equal to Q1 by 4 pi epsilon naught into distance. Now distance from this to this is R2, and Q2 divided by 4 pi epsilon naught, this is the radius. So potential difference between inner and outer spherical shell is V1 minus V2. So look at this, this is the V1 and V2. So look at this, this negative, so this cancel out. Therefore Q1 divided by 4 pi epsilon naught, this is the 1 by R1 minus 1 by R2. So if a conductor is connected between the two cells, charge always flow from inner shell to outer shell, whatever be the charge in the outer shell. This is the principle of Venn diagram generator, that charge always flow from inner spherical shell to outer spherical shell. This is same as NCERT problem 2.36. Okay. Now look at this. This is the schematic diagram of Venn diagram generator. Look at this. This is a moving belt. Now a metal brass is very close to the belt and it is connected to the source of charge, that is the generator. Charge from the generator reaches to the metal brass, and this metal brass discharges the charge on the belt. Now this belt gains charge. As belt moves this direction, so charge also moves this direction. This is another metal brass which is in contact with the inner surface of the large metal sphere. So look at this. This charge is gained by the metal brass and it is connected with the inner surface of the big sphere. So this charge quickly transferred to the outer region. So the outer surface of the Venn diagram generator increases. So after a few moments, the charge of the Venn diagram generator is so large that it produces a potential difference a few million volt. Okay. Now next, the potential of the Venn diagram generator is 15 into 10 to the power 6 volt, and the dielectric strength of the medium surrounding the Venn diagram generator is 5 into 10 to the power 7 volt per meter, what will be the radius of Venn diagram generator? Now we know E equal to V by R. Okay. Now look at this, R equal to V by E. So look at this here, V equal to 15 into 10 to the power 6, and this is the 5 into 10 to the power 7. So this is the 15 by 50. So look at this, this is the 3 by 10. So this is the 0.3. So radius of the Venn diagram generator is 0.3 meter or 30 centimeter. Understood? Many thanks for watching this video. I hope this video will be beneficial for you for your preparation in NEET, MEN and CBSE. Please like, share and comment on this. And if you are new, don't forget to subscribe my channel.